All right, thank you. Thank you all for coming back. Let's continue. I'll just pick up where we left this morning. So we covered already quite a lot of ground. Told you about spin qubits and spin qubits, about exchange coupling, decoherence, nuclear spins. So this is a form of magnetic noise. And I was trying to show you that if you get rid of nuclear spins, this can lead to very long coherence in some materials. Prime example being silicon. There are also other examples, carbon, germanium. So these were sort of materials issues. Okay, so although we covered a lot of ground, my plan was too ambitious. I was trying to cover about twice as much material, so I guess that's normal. And I think it's okay. So I rearranged the plan a bit. I will continue because I think this is important. Next I want to talk about multi-spin qubits and how they can, first of all, how they allow for all electric spin control and quantum gates, and how they, in this sense, couple to electric fields, which is both good and bad. You have to, you get this additional control now, but also potentially you open a channel for decoherence. And then I decided to move the part about 2D materials and spin physics and Valley physics and the defect spins to tomorrow's lecture. All right, so let me just start again with one just very basic slide, just to put things into a broader perspective, and maybe this is something you all know, but just I think it's quite good to start from a sort of conceptual, very fundamental point. So the electron spin couples to magnetic fields via its magnetic moment. So this is, this is the Zeeman term in the Hamiltonian of an electron. And there's this magnetic moment which is proportional to the spin. So although this intrinsic spin means that there's an angular momentum, but it doesn't correspond to a moving charge, it's an intrinsic angular momentum, it still gives rise to a magnetic moment, as if there was a moving charge. And so this coupling is not so strong, but it's strong enough so you can do things like electron spin resonance that we've seen yesterday. So this coupling, if you express it in sort of appropriate units for semiconductor physics, it's about 10 to the minus 4 electron volt per Tesla. This is the Zeeman splitting you get. For every Tesla you get 100 micro EV. This is if the G factor is exactly 2. In some materials, the G factor is not exactly 2, and then this number is modified. Okay, so then in principle, from very fundamental considerations, it would be allowed, even in the standard model of particle physics, I think it would be allowed that the electron spin also carries an electric dipole that couples to the electric field directly. That would be something like this. And people have been looking for this because it would break some symmetries. It would be interesting to know about this, but actually, so far, people have not found any electric dipole of the electron spin intrinsically. So the experiments, actually, there are some recent experiments that are quite fascinating. They limit the value of this to 10 to the minus 30 electron charges times meter. So this is a tiny boundary, and so for all practical purposes for us, we can assume this number to be 0. So the electron spin does not have an intrinsic electric dipole. If we want to couple the spin to an electric dipole, it basically will have to do somehow with the motion with the electron. So we have to couple spin and motion, and there are several ways to do that. So, of course, a moving electron has an electric dipole, so this is the but this has nothing to do with the spin, right? So this is the concept of an antenna. If you have a moving electron, there's an electric dipole. It can radiate or it can be excited by radiation. And this is basically the electric field. But what's missing is the connection now between position and spin. So to make this proportional to the spin, there would have to be a connection between this position operator and the spin. And for one single electron, what can do this is the spin-orbit coupling. So this is still kind of non-relativistic Hamiltonian, and of course you know that the separation between magnetic and electric fields in relativistic theory is not exact, so these two are actually transforming into each other. So if the electron is moving fast enough, then basically there will be a small component of the electric field in here and vice versa. And in practice, how we describe this is using the spin-orbit coupling. So there's basically this effective magnetic field is proportional to E cross P. So this is the electric field vector product with the momentum of the electron. This gives rise to an effective magnetic field, and this is then what couples to the spin. Another way of coupling the position to the spin is if we apply an inhomogeneous magnetic field. This means that basically this B becomes B of R, and so I can expand this B of R in R. So if my electron moves, it starts seeing a different magnetic field. So B of R and some B of R naught plus delta R times gradient of B at R naught, right? So if you plug this into the Zeeman energy, then you get something that couples the spin to the position. So this is this term. So if you apply an inhomogeneous magnetic field, you can effectively couple position and spin, and via this coupling, then you ultimately couple electric fields to the spin. Okay, so these are two methods that are being used for electric control of spin qubits, and these work for single electrons. You can also go beyond one electron, and then you have an additional effect that couples spin and position, which is the Fermi statistics, which basically tells you that the total wave function, including spin and position of an electron or of a number of electrons, has to be anti-symmetric. So basically this also connects spin and position, and an expression of this is the Heisenberg exchange coupling that we've seen this morning. Because, you know, basically this exchange coupling depends on the tunnel barrier between two sites, and the tunnel barrier in turn can depend on the electric field. It just controls the height of the barrier, and then you see that here the spins here are coupled to an electric field in a slightly different way than here. So all of these can in principle be used to do electric control and maybe Cavity-QED with electric fields using spin qubits. All right, so let me pick up where we left this morning. So I have this fast exchange coupling, and I have a slower one-qubit magnetic control, and I would like to replace that with electric control. And I've already mentioned that there are some single spin realizations. So this is the example with spin-orbit coupling. There are examples with magnetic field gradients. This has all been realized in experiment. So the simplest first step you can make to make use of more than one electron is that you represent one qubit by two electrons, or the spin of two electrons. Let's say if you have two quantum dots and you have two electrons, what we would previously call two qubits, we now call one qubit. So we are not using the entire Hilbert space. We have 4 spin states. We only pick 2 out of those 4. And actually, what we can do is we pick the spin singlet as the qubit 0 and the spin 1 of the spin triplet as the qubit logical 1 state. And you can pick here either the SC equals 0, so then these two have the same projection along the z-axis, or you can pick a polarized state here. I mean, both has been explored experimentally, both has its pros and cons. I'm not going to go into details here, but basically what this will buy you is that now you can draw a new Bloch sphere. So this is now not for a single spin, but for this 2-spin or singlet-triplet qubit, where the north pole is the singlet, south pole is the triplet, and then somewhere on the equator is the up-down state. Here's the down-up, and here will be, here are all the linear superpositions of up-down and down-up. Okay, and so what you can do now is by applying exchange coupling, you change the energy splitting between singlet and triplet, as we have seen. So it means you change the energy between this state, and that's like applying a magnetic field. If this was a single spin, this would be the same as applying a magnetic field along the z-axis. So basically, this exchange coupling acts as if you would apply a magnetic field along the z-axis, and so basically, this exchange coupling can now give rise to single qubit rotations. And this is an electrically controlled single qubit rotation. That's not enough, though. For quantum computing, you need rotations about at least 2 orthogonal axes in order to generate SU2. So if you want to make rotations about an axis which is orthogonal to this, let's say some axis which points into the xy plane, this cannot be done with exchange, because for this means that you could rotate the triplet state here up into the singlet state by making a pi rotation about this axis. And this would mean that you change the total spin. But it's obvious from this Hamiltonian, this commutes with total spin. So it means that total spin is conserved when you do exchange coupling. And therefore, there's no operation that involves only exchange coupling that takes you from here to here. And so that you cannot make rotations about this axis or any axis in the plane. Actually, in fact, any axis that's not the z-axis by using only exchange. So for this, you need something different. You need something that breaks spin conservation symmetry. And actually, one thing that works is, again, a magnetic field gradient. So if you have a magnetic field that's different on the left and on the right dot, then this field gradient or difference field, this will drive rotations in the singlet-triplet space, basically taking you from triplet to singlet and vice versa. And with these two ingredients, you can then, in principle, generate any rotation of a single qubit. And this is still a spin qubit, but it's now controlled partially with electric fields, because this exchanges coupled is controlled electrically, but still there is some magnetic control required here. So then, of course, this begs the question: can we do better? Can we do everything electrically? And this leads us to the exchange-only qubit. So the question is this possible? I would basically, when I look at this Hamiltonian, I know that this is the one that I can basically generate more easily than this one. Can I do everything with this one? And this doesn't work with qubits consisting of a single electron spin, because this term here conserves the spin, the total spin of our system. And it also doesn't work with singlet-triplet qubits, again, because this term conserves total spin. However, if I go to 3 spins per electron, per qubit, then actually it turns out that this is sufficient. And the reason is quite easy to see. If you add 3 spins 1/2, you obtain here this sum of representations of SU2, and actually you get the 1/2 representation twice. So what it means is that you can pick now one state from here and one state from here with the same SZ quantum number. And these are 2, and here they are expressed in terms of product states of the 3 spins. And what it means is that now you have 2 states that have exactly the same spin quantum numbers. And this exists only for 3 or more electrons. And so basically these only differ from each other in terms of permutations of the spins and not in terms of the total spin. So this means, in principle, there's nothing that prevents this interaction to make arbitrary operations between these 2. And in fact, you can show, and I will show you in a minute, you can show that this is possible. So the idea is now that you can get rid completely of the Zeeman interaction of using local magnetic fields. You can work only with this exchange coupling. And coupling, you basically represent every qubit by 3 spins, shown here, and then you would, for the single qubit gates, you would operate exchange coupling internally between 2 of these 3 spins, and for 2 qubit gates, you would operate exchange coupling between spins belonging to different qubits. And so one can show that this works. For single qubit gates, it's quite easy to see. If you apply the exchange coupling between spin 1 and 2, it turns out you get rotation about an axis that's pointing in this direction. And when you apply the exchange between 2 and 3, you get rotations about another axis, which is not collinear. It's also not orthogonal to JL, but they actually enclose an angle of 120 degrees. But that doesn't matter. So it just means that you cannot immediately apply Euler angle construction to generate SU2, but you can, as long as these are non-collinear, you can always find sequences, and in this case, I think it takes at most 4 exchange pulses to make any rotation in SU2. And this actually has been shown experimentally. So people have looked at 3-spin qubits. These 3 experiments are in gallium arsenide dots, and the 4th one is in silicon quantum dots. And so this is a picture of state tomography. You see the Bloch sphere here. And this is the starting point, and there's a rotation that should go around the greater circle here, but of course, because of decoherence in this case, it's spiraling inside. Okay, so these are 1-qubit gates, but we also need 2-qubit gates, and that's a bit more complicated. I'm not going to show you the entire story here, but it turns out that when you apply exchange coupling between these 2 spins, then you actually go out of the logical Hilbert space that's spanned by the product of these 2 states for these 3 spins and the 2 states for these 3 spins. Because exchange now only, this exchange coupling conserves the total spin of all 6 electrons, but not of the 3 electrons separately. And so actually so when you start applying exchange here, so this is again a circuit diagram. Remember, this is a space-time diagram. Here are the 6 spins. Here, these are spins, not qubits. And to the right is time. And so you start by applying exchange here in the center. Actually, what this does is it takes you out of this 4-dimensional logic Hilbert space, and then you have to be careful to do something to get you back in, and still, in the end, do something non-trivial, which is equivalent to controlled knot of the 2 qubits. And this, okay, this is a problem you can solve numerically, and we found numerically that there is a solution to this. But then, I mean, maybe it was a bit of a mystery how this solution comes about, and there was actually quite amazing work by a group of mathematicians in Japan who solved a 69th degree polynomial equation to show that these are really algebraic numbers. So these are really solutions of such an equation, and these exist, you know, in some sense to arbitrary precision. There are also other improvements. You can apply pulses in parallel. And there are other things you may want, but I think I'm going to stop discussing this here. So this is an interesting problem, and maybe there are still improvements possible. We don't know. So but it becomes important if you would want to do universal quantum computation using these exchange qubits. Okay, so there are actually different versions of these qubits by now. There's what I just described to you is what we call exchange-only qubit, where the exchange couplings are essentially turned off whenever you let the qubit register rest, and it's not supposed to do anything, and you only pulse it when you want to apply a quantum gate. Then there's other implementations where the exchange coupling is always turned on. So one is the hybrid qubit, so-called hybrid qubit, where you put 3 electrons in 2 quantum dots. So you can work with the same 2 states of 3 electrons, but you put them not into 3 quantum dots, but 2. This means you cannot really control both of these exchange couplings directly, but it can be shown that you can still do universal quantum computing. This is something that has been pursued extensively by the group of Mark Erickson at Wisconsin. Another version is where you keep the exchange coupling on, is what is described by these 3 papers here. This is a group of Charlie Marcus, and they basically decided that for them it was good to have always an energy splitting between the 2 qubit states. So in this case, the energy splitting between the qubits, if the exchange is off, is 0. But in this case, you have an energy splitting that you can address resonantly with electric fields, with AC electric fields, and then this is called resonant exchange qubit. So basically, when you keep these exchange couplings always on, you can, by changing the 2 together, so if you keep them on all the time and then you change the magnitude of JL and JR at the same time, you get rotations about this axis, and then if you change the difference between the 2, you get rotations about this axis. This you can do resonantly. This is again as kind of a magnetic resonance setup where you have a fixed field. You can have a small oscillating field here. So you would here apply a small oscillating difference field to make transitions between the 0 and 1 state. Then there are also asymmetric versions where the tunnel couplings here are different. And then there's another version where basically, which is similar to this one, it's a mixture between this one and this one. Okay, let me summarize these different qubit types. So we have spin 1/2, 1 electron per quantum dot. The qubit states are just plus minus 1/2, spin up and spin down of the single electron. Then we have singlet-triplet, where you put 2 electrons each into a separate quantum dot, and you pick the singlet and one of the triplet states as your qubit states. Then we have this exchange only and RF exchange qubits, where you put 3 electrons in 3 nearby quantum dots, and you use 2 of the 8 spin states that have the same quantum numbers. And this allows for all electric control. And then there are some spin charge hybrids. You could put the 3 electrons into 2 quantum dots. This is the hybrid qubit. You can also put all 3 electrons in 1 quantum dot. This is what we call spin charge qubit. Okay, so let me go back to this point that I just made before, that for this resonant exchange qubit, so that seems to be an implementation of this qubit that's been studied quite a bit. And so basically, let me repeat again how it differs from the original idea of this exchange-only qubit. The exchange-only qubit, basically whenever you don't operate on the qubits, the exchange couplings are turned off, the 2 qubit states are degenerate, and there's no electric dipole. So if these exchange couplings are off, in the absence of spin-orbit coupling, there's no electric dipole, and this qubit is completely safe against electric field fluctuations. However, for this resonant exchange qubit, you keep the exchange couplings always on. This just makes it ready for this RF driving, kind of magnetic resonance driving, which is very convenient. But also it means that this qubit is permanently endowed with an electric dipole. There will be an electric dipole, and I will show you that this is the case. And actually, electric field fluctuations should then also be able to decohere this qubit. And so this is something we worried about, and we thought we should go into and look into. So this always-on exchange adds charge character or electric dipole to the qubit, and then it means that low-frequency charge noise, for instance, that could come from fluctuating defects or noise that comes from the gates. So these gates that control the energy levels of the qubits and the gates that control the tunnel couplings between the qubits, they are connected to outside pulse generators at room temperatures at some point, and there will be electric noise. In particular, if these are supposed to be fast gates, then there will be a wide bandwidth control, and basically there will be noise here. So all of this noise can affect now this qubit. So how do we model that? So this is a kind of a typical theory question. What do you expect? How this qubit is behaving under electric noise? So basically, the picture is the following. If you look at the energy splitting, so here's energy or frequency. This is energy splitting between the 2 qubit states as a function of the external parameter. This parameter could be one of the voltages or one of the tunnel couplings that's voltage controlled. And of course, when you change these, then this energy will change in some way, and this is something we can model. And so basically, when one of these parameters is fluctuating, say V1 is fluctuating about its intended value, say here, then you would have some jitter here on the horizontal axis, and this would translate then into some jitter in the vertical axis in the qubit energy. And if these fluctuations are small, I can make a Taylor expansion of this fluctuation in the qubit energy here. It's just basically a Taylor series where I have the derivative of this energy with respect to this voltage times the voltage fluctuations in this port, and then I do this with all the different inputs, and I can go to higher order. And this gives rise to dephasing, because if the energy splitting fluctuates, this will mean that there will be a random phase that is accumulated. And this I can see, typically the way to measure this, to see this, is a Ramsey in free induction decay, which means you prepare the state in superposition of these 2 qubit eigenstates, 0 plus 1. You see I'm probing now something like T2. I'm assuming that there's no relaxation, so there's, basically I'm only interested in the effect of these energy fluctuations. And after some time, this state will have evolved into a state where the phase in the one state, so there's no transitions, but there will be a phase which is simply the integral over this total energy. And this part of the energy, this part omega, this is well defined. I'm not interested in that. That's the sharp phase, but there's this fluctuating part of the phase which is accumulated due to noise. And so this is something that if I average here, so here I have to average over the noise realizations, and this will give rise to decoherence. So basically, I can average this phase here, and if this is Gaussian noise, I can use a first cumulant theorem, and so basically I get an exponential. So this will, okay, depends on the noise spectrum now, but typically what happens is that this has the form of a Gaussian t squared divided by some time squared. This is the dephasing time of the qubit. So basically this average here, this tells me how the off-diagonal elements of the density matrix, or basically this coherence here, decays over time, and this T phi is the decoherence time. So if basically I want these fluctuations to be as small as possible, and there's a trick and I think this was used very heavily, and this was first used, maybe not first, this was definitely used in superconducting qubits, probably it was used even earlier in atomic clock transitions, where basically you try to identify points where these fluctuations is smallest, and these points are basically where this lowest order of the fluctuation vanishes. So even if this delta V is not zero, this can be zero if the derivative of omega with respect to V1 is zero. So basically if I'm here at some minimum or maximum, like here, then a fluctuation in this direction will translate only into second order fluctuations in the energy direction, so which means I get rid of all these first order terms. And this is what we call sweet spots in parameter space. And I can try to identify points in parameter space where my voltages are set in such a way that I'm sitting at such a point where some of these derivatives are zero, or ideally all of them are zero, and I have only then higher order fluctuations. And so this is something you have to do basically if you open your system to charge fluctuations in this way. It's also a concept you can do for other fluctuations, but here it's specifically useful for charge fluctuations or electric field fluctuations. So, okay, so in order to do this in practice, you have to find this qubit energy splitting as a function of these parameters, and this is a simple exercise in some sense. It's you can model this system as a three-side Hubbard model, so it's just three sides where electrons can sit. You have an on-site Coulomb repulsion here with this Coulomb energy U. You have a potential in each dot given by these voltage gates. You can have also nearest neighbor Coulomb interactions, and you have hopping of electrons between nearby dots. So this is a simple model that captures basically the physics of this three-dot system, and that allows us to calculate these energies that we need to find the sweet spots. Just to show you how we parameterize this system, let's forget about the tunnel couplings. Let's look at these three voltages. You can set these three voltages independently to set the energy levels of the three dots. Of course, there's one combination of these three voltages which doesn't really affect the qubit, which is if all the voltages are changed simultaneously. If you increase all of them in parallel, basically, you change the total energy of the system, but you don't change any internal dynamics. So basically, that is not interesting, and we can parameterize the remaining 2 degrees of freedom by what we call epsilon. So this is basically the tilt angle here in energy space between the outer dots, and delta, which is the energy of the center dot relative to the average energy of the outer dots. So these two are really two relevant electrostatic parameters, and that's also what the experimentalists use in their experiments to describe the system. And so now you can basically you can take your qubit states, and then we have to include doubly occupied states, and actually the ones that are directly coupled in this regime of the Rx qubit. This is a regime where the energy of the center dot is high enough such that it's never doubly occupied. you have just 4 levels, so it's just a 4x4 problem. You can diagonalize it, you can do perturbation theory. What you get in the end is this energy, qubit energy, as a function of these tuning parameters, epsilon and delta. And so you see there's a valley, an energy valley here, and there's a saddle point, and this has basically 0 derivative in both directions, so this is a so-called double sweet spot. And for a totally symmetric system, this would be at delta equals epsilon equals 0. If the dots are asymmetric, so if the tunnel couplings are not the same, this moves away from this center point. So basically, this proves the existence of a complete sweet spot for the operation of this in the presence of charge noise. So this is this Hamiltonian that you can simply diagonalize it. You can also do a Schrieffer-Wolff transformation to get an effective Hamiltonian for the low energy part. So it's a fairly simple problem. Okay, then you can also actually, so you can find out where the sweet spot is. You can also calculate the dephasing time for every point in parameter space. If you're at the sweet spot, these lowest order terms vanish. If you're not at the sweet spot, you have to take them into account. And so this we did. And what you can find is now, so what we plot here is the dephasing time. So up here, this is more coherent, this is less coherent. And this is the fluctuation amplitude of the electric noise in epsilon and delta, which we set equal here. And so basically, we believe that it's around 10 to the minus 3 milli-electron volt at the moment, or maybe this is last year or 2 years ago, where it turns out that the potential is sufficiently flat out here. And so, okay, basically, maybe I should say, so if you're at the sweet spot, then the dephasing will be limited by the second derivatives of the energy splitting of the qubit. And this means this is the curvature of this energy potential in this direction and this direction. And you see that in this direction, the curvature is quite sharp. And so actually it turns out that you can go out to some flat space out here. And even though you have these first order terms, you can, with the noise that we have now, basically you can beat, so you can get a longer coherence if you go out here and you're not at a sweet spot compared to being at a sweet spot where this curvature is relatively high. But now if you decrease the noise, so if we manage to improve the quality of the control in the sense that of filtering, there will be a point where, because this scales, if you're not at the sweet spot, the noise, the dephasing time controls scales like 1 over the noise amplitude, whereas if you're at the sweet spot, it's 1 over the noise amplitude squared, simply because these are square terms. And there will be a crossover where you win at the sweet spot. And okay, this seems quite low here. You can move this crossover further by making the potential softer. And we found that this can be done by increasing the tunnel couplings between the dots. So, so basically this gives us a perspective, and also it tells us where to operate this qubit. I briefly mentioned other qubit realizations, and they are actually in a different part of the parameter space. So this resonant exchange qubit is somewhere close to the, so it's in a regime where you have one electron in every dot, so 1, 1, 1 means 1 electron left, center, and right, and this 2, 0, 1 means 2 electrons left, 0 in the center, and 1 right. And so this Rx qubit operates around here. You can also go to other parameter spaces, other places in parameter space, and actually we reparameterize then this center dot potential, and basically the exchange only qubit is here in the center, where you're really deep in the 1, 1, 1 regime. And you can also go to regimes where you have 1, 2, 0, so one of the side dots is not filled, so basically you put 3 electrons in 2 dots, and this is the well-known hybrid qubit. So this theory for charge noise also applies to other 3 electron spin qubits. So we can basically find sweet spots and calculate dephasing times for all these 3 spin qubits. We can also find other double sweet spots. So here there's some symmetry there, they occur several times. And so here's, of course, I mean, okay, let me show just one picture of dephasing. We can also calculate the dephasing time now, assuming noise, some amplitude for the noise and for the tunneling. And so here's basically, you can identify some areas, some lines where we have particularly long-lived coherence. And some of this was known before, so there was a sweet spot here was known before, but we basically just explored this entire space. And you can change, so if you increase, you either decrease noise or you increase tunnel coupling, then the potential will become softer, the noise will become weaker, and you can increase the dephasing time. Okay, and basically what you can do with this model is you can analyze the noise due to all of these different noise sources separately or combined. So I'm not going to go through all of these. Okay, this is basically a zero temperature calculation. It depends where the noise comes from. This, in principle, could also be thermal electric noise, right? So this is not excluded. But what we assumed here is just there's some noise amplitude, and we didn't associate it with the temperature. Yeah, so I think we can get most of these, or I think all of these parameters from experiments. So these tunnel couplings are known from the experiment, and the noise we also have an idea from the experiment. So that's not so easy to get, but we have some idea from the experiment, at least more or less the order of magnitude of the electrical noise. And so I think basically and also this charging energies, I think we basically get all of these parameters from independent. Okay, so now I'd like to switch gears a little bit. I've talked about basically negative side effects of electrical control. So you attach an electric dipole to your spin qubit, for instance, in these multi-spin qubits. This allows for electric control. This is good, but it also opens new decoherence channels due to electric field fluctuations. Another positive effect is potentially that you can couple such spins to an electromagnetic cavity via the electric field rather than the magnetic field, which usually means that the coupling is much stronger. And so this was, we started thinking about this about 10 years ago when there were some really groundbreaking experiments. One was from Yale, where they really pioneered these superconducting resonators that we have heard a lot about at this workshop. So these basically showed that you can couple remote superconducting qubits very well, and basically you can do very nice Cavity-QED. Also, these superconducting qubits have very high electric dipoles, very large electric dipoles that allow for very strong coupling. On the other side, you have the semiconductor spin qubits, which allow for long coherence. I mean, maybe not in these initial experiments, but we have, I think, seen, or our hopes have been basically proven right, that by good materials engineering, people have been able to increase this coherence time for spin qubits by a large amount. And now it would be interesting to combine these two things and try to couple spins to electromagnetic cavities. So there's basically there was the first idea to couple singlet-triplet qubits, which have an electric dipole, to superconducting resonators. And the idea is as follows. So basically, imagine you have a double quantum dot with two electrons. It has an electric dipole. Essentially, this spin singlet has an electric dipole, and the spin triplet has no electric dipole because of the Pauli exclusion principle. Then if you want to make transitions between the 0 and 1 state, so the singlet and triplet state, as you know, you need a magnetic field gradient to break the conservation of the spin conservation to make electric dipole transitions possible. Actually, it turns out there's another symmetry you have to break here. Spatial inversion needs to be broken here in order to break inversion symmetry, because electric dipoles transitions are always between an even and odd state in space, and if you're at if the two dots are at exactly the same potential, turns out that basically this electric dipole transition is forbidden. If you calculate the electric, the coupling between the spin qubit, between the singlet-triplet qubit, so the transverse coupling, then what you get is basically something which is proportional to the exchange coupling. So it's basically, okay, here you have the vacuum electric field of the cavity, and the rest is essentially the electric dipole of the double dot. So this is E times A is A is the distance between the qubits. So this is basically the unit, the maximum electric dipole you could get from a charge that moves. Okay, just a minute. And then the rest is basically the difference between charge and spin. And this involves exchange, and it involves this magnetic field gradient, and it involves this breaking of the inversion symmetry. Yeah, what's this? I mean, the singlet, it's just because I'm drawing the singlet like this. It just means that this can move. If you apply an electric field, this electron can move to the other dot. Yeah, that's all. And the triplet doesn't have that because of exclusion principle. Okay, so this is just the result. I'm not going to show you the calculation. But basically, this was some idea, and we speculated that a coupling which is not as strong as a coupling of a charge, but still kind of reasonably strong coupling would be possible. More recently, because people have been also interested now in these 3 electron spin qubits which can be completely controlled electrically, and there's some efforts underway in basically embedding them into electromagnetic cavities, superconducting resonators. We have also modeled these systems, so Cavity-QED RX qubits, and this is also strongly motivated by recent experiments showing strong coupling for charge in double quantum dots. So there are 3 experiments. I think I have a separate slide for this, that all showed almost simultaneously the strong coupling regime of Cavity-QED for a single electron charge in a double quantum dot coupled to a superconducting resonator. And the difference between the experiments was essentially that in the Princeton experiment, the double dot was a silicon germanium dot. In the Paris experiment, it was a carbon nanotube. And in the ETH Zurich experiment, it was a gallium arsenide double dot. There was also quite a lot of difference in terms of parameters, but maybe I'm not going to go into this here. Okay, so basically when you can also set up a model where you have a cavity and you're trying to couple the 3 electron spin qubit to the cavity, and then basically you can use your electrostatic parameters to control not only the exchange coupling or the qubit splitting, but also the electric dipole, just in the same way you do it for a double dot. And so here's an example. So the cavity coupling in this case is again, essentially the scale is given by the vacuum electric field of the cavity times the electric dipole. So it's E times the size, the total size of the system. So the biggest distance an electron can travel here. So this would be sort of the maximum coupling, electric dipole coupling that a single charge could experience. But now we're of course not asking about the charge, but about our 2 spin qubit states. And so that's a bit different. And this you can calculate, and then again as a function of these tuning parameters epsilon and delta, or here it's called epsilon m, you can calculate the cavity coupling in units of this charge cavity coupling. And you can see that you can strongly tune from points where the cavity coupling is very strong, so where an electron is very mobile, to other regimes where electrons are basically stuck and the coupling is very weak. And I mean, this is also clear if you look at the example of 2 quantum dots. Imagine that you make, let's say, epsilon very large. So this is epsilon in the case of 2 quantum dots. And basically both electrons would be here in the singlet case, and there would basically be no motion between the 2 quantum dots. And here in this case, the coupling would be essentially 0. Whereas if you go to this point, the coupling would be large. And so what I'm showing here is just a generalization for these 3 spin qubits, where the mobility of the electrons is a bit more complicated, and it depends on both the parameters controlling the tilt energy between the outer dots and the energy of the center dot. Okay, and so I mean this This is basically the perspective that we have, that eventually one could do a Cavity-QED with these qubits, and this would allow us then to couple not only nearby with this very complicated exchange sequence, but also over a longer distance using these superconducting resonators. And again, I mean, this has been very strongly motivated by these 3 experiments. And you can see that these experiments are quite different. They're all at low temperature. The material system is different, as I mentioned. The cavity frequencies are similar, so that all this is between 5 and 10 gigahertz. But the couplings are very different. So in the silicon case, the coupling was a few megahertz. In the ETH case, the coupling was very strong, and they needed this. So they're very good at making very good cavities. And actually, this coupling in some sense needs to be high, because this is essentially 1 over T1 here. So this is basically the spin relaxation here is or the charge, in this case, charge relaxation is very fast. So you have to compensate this, in order to reach strong coupling, you have to compensate this with a very strong coupling. And then finally, the Paris experiment is again similar to the Princeton experiment. Of course, the holy grail would be to couple very strong coupling. These techniques for the resonators they used here with a very coherent double dot system. And of course, we can hope once we can couple spins and not the charge, that the coherence anyway will be much longer than here for the charge. Right, so gamma is essentially 1 over T1. So it means T1 is very short. G squared over kappa gamma is not the same, but in all cases, I think it's sufficiently, I mean, when I say strong coupling regime, I mean, G has to be larger than, okay, I guess, well, you can compensate, right, okay, so maybe I should, you can use this, right? Or bigger, or much bigger, I don't know how much bigger it will be. I don't think they're the same, but the reason why it works here is because G is large. The reason why it works here is mostly because gamma is small. So that's my understanding. These are charge qubits. So we're not quite there yet. We don't have strong coupling between spin qubits and an electromagnetic cavity. But that's sort of where I want to go. And I think, after having said this, I think in principle it's possible. But of course, it's an additional difficulty because the coupling will be smaller, unless you make it already bigger here. Okay. So let me move to another sort of related topic. I want to say this here because it fits in. I'm talking about the same system, silicon double quantum dot embedded into superconducting resonator. And we already know that in silicon there's this additional degree of freedom, the valley splitting, which I will also talk about later. I mean, one problem is that this valley splitting is unknown, or at least there are different ways of making silicon quantum dots, and in the silicon germanium quantum dots, it's very hard to control the valley splitting. So basically, you just get a sample, and then you don't know what this valley splitting will be, and it can even vary from dot to dot. And it's very small. Typically, these valley splittings are between maybe 50 to 200 micro eV, and those are energy scales that are similar to temperatures, even at cryogenic temperatures. So it would be very good to at least know what these valley splittings are. And these valley splittings are hard to measure in transport. So if you have here your double quantum dot, you have source and drain lead, and you just try to run a current and see in transport spectroscopy where these two levels lie. The problem is that these Fermi distributions in the source and drain, they're going to be smeared by temperature by as much as the splitting or more. So then basically this entire spectroscopy blurs. And our idea was to use the microwaves in a superconducting cavity to read out this energy splitting. So let me just talk about this for a minute. So what we proposed to use and what was then later implemented, so this is the theory proposal, this is the implementation. is to use a double quantum dot in silicon germanium with this unknown valley splitting. So you have here one quantum dot left with the ground state valley level and then some excited state valley level, and you don't know this splitting. And you have another quantum dot on the right which has a different splitting. And you can tune the two dots again with this energy detuning. And now we're not looking at transport for the time being, but we're looking at, we're imagining that we embed this system into a superconducting resonator whose electric field will couple to this. So basically this electric field will bias this epsilon, will give us a kind of a tune this tilt, and we'll use this to try to probe these valley splittings. Okay, how does this work? So basically we have a cavity around. We send in some microwave, which is resonant with the cavity frequency, and then we see how much is coming out, how much is being absorbed. Okay, so basically the theoretical framework, which is quite simple and useful here, is called input-output theory. I think it's one of the least descriptive names for a theory. I think any theory should have an input and an output, otherwise it's not a good theory, but it's called like this. And so basically what you do is, and I think this is something that you have done here maybe last week. So this has occurred before. So basically what you can do is you describe your system with a Hamiltonian. So here's your cavity Hamiltonian in the rotating frame of the probe field. So omega naught is the cavity frequency, omega r is the probe frequency, A and A dagger are the annihilation and creation operators for the resonant cavity photons. Then my electronic states are these n's and m's. These are the eigenstates of the electronic Hamiltonian here. And I just define these operators, these basically projection or transition operators. And I can write in the diagonal form, I can write my free Hamiltonian of this double quantum dot just basically as projectors on the eigenstates with some eigenenergy, and then in the rotating frame. I should mention that there's a certain subtlety, because here we are dealing with more than two levels. So maybe you have seen the rotating frame for two levels. So if you excite a two-level system with a field with frequency omega, then you can transform your Hamiltonian to a rotating frame and get rid of the time dependence in the Hamiltonian by rotating this excited state with the frequency omega. And now the problem is if you have more than two states, and then you can probe all these transitions. Frequency omega, of course, you can rotate this one with omega, this one with 2 omega, this one with 3 omega. But then the problem is, let's say, what happens if you have a transition from here to here, which is also with omega. This is, of course, off-resonant, but still it could matter. And then, okay, then you see that then this transition matrix element will not be time independent. So with the simple rotating wave approximation, in general, you will have a problem. What we did is basically we neglected these. But I think one can do this even more general. So this is basically why this is n omega r. This just describes this rotating frame in the order of energy levels. And then there's the interaction, which you can write in the eigenbasis of the Hamiltonian is simply given by dipole matrix elements between eigenstates, and then these transition operators. Okay, and so then you can, treating this as an open quantum system where you have an input and output. This is, I think, something that you have seen in the course of this workshop several times. A simple way of doing this is looking at the equations of motion, because this is some kind of linear system. Look at the equation of motion of the cavity photon operator and the transition operators here in this system, where you have some effect of the Hamiltonian here. You have cavity loss, and you have input and output parts, and you have, this is from the interaction, and the same you do for sigma. This is the Hamiltonian part, this is the T1 decay, this is again the dipole transitions, and here what comes in is the occupation probability. So here you replace basically operators by numbers. These are just occupation probabilities. And in the equilibrium case, we're going to replace this by just the Boltzmann distribution, this level scheme. So this is just the Boltzmann distribution in the equilibrium case. And then we're looking for the stationary state, so we're setting these to 0. And then we can solve for sigma, we can plug it back in here, and we can get basically A, the output field. And this is the result. So here you see that you have the detuning, you have the cavity loss, and here you have the electric, what comes in here basically is the electric susceptibility of one electron going back and forth in a double quantum dot. And so I didn't write it here. The next slide. Sorry. So here you see this electric susceptibility simply given by the dipole matrix element and the population difference between the states. And then there's a resonance denominator. So maybe I can explain this in simple terms, what happens. So here's an energy level diagram as a function of the detuning epsilon. So again, this detuning epsilon here is the energy detuning between the two quantum dots. And so if you have states on the right and you increase epsilon, their energy will go down. I think it's probably exactly opposite. So basically, if epsilon is large, then the energy on the right is going to be low, and the energy on the left is going to be high, and there's just some linear tuning. And you have always two states. This is the lower valley state and the upper valley state. And at some point, two of these levels can become resonant, and then, let's say here, the green and the blue level become resonant, and then they split by tunneling. At this point, the tunneling can split the levels. So basically, at this point, where you have this curved part of the energy level, this is where an electron can move. And so actually, you can understand the first derivative of energy with respect to epsilon or electric field. This is essentially the electric polarization of our system. And the second derivative of this curve is the electric susceptibility. So basically, at these points where you have some curvature, this is where you expect to see some absorption. And now you see that, this curvature will appear when two levels cross, here, 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 and here. And the position of these crossings is determined by the two valley splittings. So it means that the absorption will happen at values of epsilon which are determined by the valley splittings. So here's a plot of the absorption, the microwave absorption. Actually, this is the transmission. So one means, black means full transmission, and here, the brighter the color, the more absorption we get. So at low, this is as a function of temperature, and at low temperature, basically only the ground state is occupied. It's blue state, and it means that only here in the center, I'm getting a feature where I can tunnel to the next step, or I can make transitions, microwave transitions to the next step. This gives rise to a big absorption peak. But if I increase the temperature a little bit, I can occupy this second level, and then I get features here and here at these positions which are determined by the valley splitting. And so these are these features, these side peaks, and they appear at finite temperature. So at 1 Kelvin, they're already very clear. Already at a quarter of a Kelvin, in this case, they start appearing. So basically, this is a prescription how to read out the valley splitting using dispersive microwave absorption. It's just, it would take a long time to really change the distribution with this weak microwave probe. I think this is a very weak probe limit where you assume that basically in this approximation I neglect all the back action of the probe on the system. Of course, you're right, there probably is this back action, but I neglect it here. And it turns out to work very well for a weak probe. So here's the experiment. So here's transmission as a function of epsilon, and indeed you see these three peaks. You can fit it with the theory. We know the tunnel matrix elements, and so basically we can really understand what's going on, and we can read off the valley splittings from this experiment. This is something we could not do with transport spectroscopy. Then the second experiment, okay, I don't have a slide for that yet.
What happens if you try to see the phase also, like the phase spectroscopy?
You can also plot the phase. I don't have it here. The phase also carries the same or similar information. I don't think I have it. I can show it. I can show it to you later. So okay, so let me just show you this final. So there's another experiment here where these two peaks are. I don't have the same strength, and so it means that this side is more highly occupied than this side. And this you can achieve if you also apply a source drain voltage. So basically applying a source drain voltage, and it's something they could do in the experiment, you can fill in from one side and you can fill in these states asymmetrically, and you get also these asymmetric states. And we can basically, in this case, what we do instead of just substituting the Boltzmann distribution for Pn, actually we solve a rate equation for the transport problem, which gives us this Pn. And we plug in that, and then that gives us the theory that describes this experiment. Yes. You could try to apply a small voltage and then just move one state after the other through the transport window here, but apparently that doesn't work very well because it's blurred by the temperature. But in principle, yeah.
By the way, are these in strong coupling regime or?
No, this is not.
This is in the. So what's the parameter regime exactly?
So I think the cavity coupling is 30 megahertz or something.
And what about kappa and gamma?
Sorry?
What about kappa and gamma?
Okay. So, I'm not sure I know all the numbers. Yeah, I would have to look up.
But it's definitely not that regime, G square over kappa.
No, I don't think it's in the, but it doesn't need to be in the strong coupling regime for this experiment. But again, this is only charge. This is not spin, right? We don't.
Right, but is it that they actually identically go to zero, or they are just neglected here?
Coherences.
Coherences.
Yeah, I think they're neglected.
They're neglected.
I mean, it's a good point that I think the coherences matter if two of these levels are almost degenerate. Then, I mean, basically, if the level difference here is smaller than the tunneling from the lead, right, then you can tunnel sort of coherently into a superposition of such levels.
Right.
And then what we're doing is some kind of secular approximation, and then I think this breaks down.
I see.
So, but I think for all cases we have looked at so far, we have been okay with our approximation. But you can do better.
Right. Okay. Thanks.
This was very quick and dirty. Just to get this. Are there more questions? Because in some sense, this is now I sort of over corrected. So I thought I would get only this far because we were so slow this morning. But I think maybe I can continue a little bit. Or you can also. No, the experiment. This was finite bias data. Sorry. Yeah, so this plot here is finite bias data. So the bias, here's the bias, 600 millivolt. This is source drain.
Is a kind of a shift because of source drain bias and all, like, or?
Sorry, what kind of shift?
Is there like a shift in the peak values, or? Oh, sorry, this is as a function of detuning, not with this.
You mean if you apply a source drain voltage?
Yeah.
I mean, it's a good point. Maybe you have to compensate. You have some electrostatic gates now, and they will have some cross capacitance. I think they compensate for that. Otherwise, probably this would be shifted. I think they sort of renormalize where epsilon 0 is. I think. No, there's no gain here. So, okay, so this is a good point that in the case where, so in equilibrium, then there can never be population inversion here, right? But of course, in non-equilibrium, when you drive a very strong current, you could imagine that there's a situation when you populate some higher levels here with more probability than the lower levels. And then you would get some population inversion, and this would give you basically gain. And in principle, this is possible, and I think we have seen it in the theory for a few points in parameter space, but we haven't really followed it up. And okay, so this bias, I think it's quite small. Yeah, so maybe you could drive harder, and yeah, so it's not something we have really explored, so I cannot say much about it. But I think it would be interesting to look at it, and it's of course related to this double quantum dot maser that has already been demonstrated. But this was basically in an indium arsenide wire double quantum dot without valley splitting, and so okay, maybe this valley splitting adds some new feature. Okay, so maybe I'll begin maybe 5 or 10 more minutes with what I was going to say tomorrow, but I think it's even better if we can cover some of that. And so basically the next topic will be spin and valley. So now I want to go a bit more deeply into the consequences of using other materials than gallium arsenide. So it could be silicon or graphene. So anything that has valley degeneracy, that has a deep impact. And so remember from this morning, we had this discussion of nuclear spin-free materials, basically column 4 elements. And so among them was carbon. And so graphene is tempting, silicon, and so on. And then I already pointed out that all of these, for some reason that I don't really understand, all of these group 4 elements seem to crystallize in crystals that have band structures with valley degeneracy. So for instance, so in silicon, you have the 6-fold valley degeneracy, which is reduced to 2 if you put some uniaxial strain, or when you make a 2D heterostructure. Same is in germanium, or similar in germanium, and also graphene. And so that's important. Actually, now maybe thinking about graphene, there are actually 2 issues that I would like to point out. And the first one has nothing to do with valley degeneracy. The first one is simply that graphene is a semiconductor without band gap. And so, I mean, maybe this is obvious or maybe not, so I'll explain it. So in a regular semiconductor, if you look at the conduction band edge, so this red line here is supposed to be the conduction band edge as a function of space. And so by using some external gates, this gate electrodes, we can shift the conduction band edge and lower it in some finite region, and this forms the quantum dot, because then there are some states in the conduction band here which exist here at this energy, but not in the barrier. Right? So this is basically the way we make we can understand quantum dots in semiconductors with a large band gap. And so, I mean, there are of course other states which are way down here, 1.5 electron volts lower, but they don't play any role. In graphene, the situation is very different because the conduction band and the valence band touch at the Dirac point. So if you try to play the same game, so you lower the potential in some finite region of space, trying to localize electrons, make a quantum dot, then what happens is that the conduction band states inside the intended dot will overlap in energy with valence band states outside in the barrier. And so this means that an electron here can actually go out through the valence band. And this is a general property of these relativistic-like particles. So in relativistic quantum mechanics, you know that there's Klein tunneling through barriers. And this is very similar. It has to do with the absence of a band gap for massless relativistic particles. So basically this means that naively, at least with this naive attempt to confine particles, this won't work. You cannot confine electrons in graphene, and in some sense it's not so surprising because this linear dispersion relation means that basically the derivative of this energy with respect to the k vector is a constant. So this is the velocity, it's just a constant. It's a bit like the speed of light for photons. And so just like the fact that you cannot stop photons, well, maybe you can, but probably there are some people in this room who can, but you cannot naively stop photons because they have a constant velocity. So you cannot stop photons with just some refractive medium or something. It's the same here. You cannot stop these electrons simply by applying a potential barrier. So this is one problem. And then, I mean, you can think of ways out of it. And already quite early on, when graphene was being studied, people have started, of course, to make this kind of brute force approach to quantum dots, just cut out graphene, right? I mean, you just cut it out, make a nanostructure where there's basically no graphene outside. Of course, then the electron has to stay in here, because in here there's graphene and outside there's nothing. But and so this works in some sense. These are nice Coulomb blockade peaks for transport through this. So there are quantized energy levels. The problem is that with these, you make here some edges, and these edges are usually causing a lot of problems. They are basically mixing the values, and they're causing a disorder. And so this is, I think, for spin qubits, this would be problematic, maybe. Another idea that we came up with was to use graphene nanoribbons, because, but this is also another proposal with edges. So if you had a way to make clean edges, for some edges actually open a band gap. So you could make a 1D gapped semiconductor with this, and then use electrodes to confine particles. This requires very clean edges, and it's probably very difficult to make. There are some chemical approaches to make clean edges, but I think it's hard. Another idea is to, okay, if you had something like, okay, so this actually this was, here's an experiment with a graphene nanoribbon with double dots. So probably these edges were not clean, but still there was a band gap. And so there's a nanoribbon that lies across here, and you see as a function of the gate here and here, you see current, and these triangles are characteristic of double quantum dot behavior. So in principle it can be done, but again I think these edges are not clean. And then the other idea is that if you have, for instance, bilayer graphene, you can electrically open a gap without edges. This is also something that has been implemented even for freestanding bilayer graphene. I think this is quite hard to make, so it's probably, I don't know, it's maybe hard to make this into a spin qubit architectures, but at least in principle, quantum dots in graphene are feasible, and it would be interesting, for instance, what the lifetimes, the coherence times of the spins would be for localized spins. Okay, the other problem I've already mentioned is valley degeneracy. So basically, in a gallium arsenide, you have the single minimum in the conduction band. Graphene, you have two Dirac points, and in silicon, you also have two minima which are gapped. So this gives rise to addition. So we have this exchange coupling story that will be changed here, because we have two states now, and basically two spins up can go onto the same dot because they have two orbitals to go into. So this entire story about Pauli blocking and so on will not work anymore, at least not as this simple way for a system with valley degeneracy. So maybe this argument I can still show, and then I'll finish. So you remember from this morning that exchange coupling has to do with the fact that the hopping of electrons onto the same dot, two electrons onto the same dot is blocked for the spin triplet because of the exclusion principle for fermions. And this gives rise to an energy lowering for the singlet, but not for the triplet. And this is the source of exchange coupling. This is the same story, and this is the source of Heisenberg exchange coupling. Now let's see what happens if you have two levels. So this would be my valley states K and K prime in graphene, or the two valleys that are left in 2D silicon. Then I have two levels here. And in some sense, I have the same physics. Some states will be blocked, and some states will not be blocked. And the states that will be blocked have some simple energy given by the single dot energy, and the states that are not blocked will have basically this energy lowering T squared over U. And the exchange coupling will, the exchange energy will have the same value. But the question is which states are blocked and which aren't. And in this case, these are not simply the spin singlet, but they are here. The spin singlet are the antisymmetric states of spin alone. And here we're talking about the antisymmetric states of spin and valley. I called it super singlet here, so this is antisymmetric spin-valley states. Here are the symmetric spin-valley states. So in the case of spin only, we have 3 states here and 1 state here, and now we have 6 states here and 10 states here. In total, there are 16 states because there are 4 states per dot. 4 times 4 is 16, and you can divide them up into symmetric and antisymmetric. And actually, the Hamiltonian is exactly the same in some sense. It's just this energy multiplied by the projection operator onto this fully antisymmetric spin-valley space. Right? So the only thing that's left to do is to find out what this projection operator looks like in terms of the spin and valley operators. Okay, so here's the story. So basically, totally antisymmetric state of spin and valley means, so I can basically separate or sort the states for the spin again into singlet and triplet. And I do the same for the valley. Basically, I define valley singlet and valley triplet, which are the symmetric and antisymmetric states for the valley. And then the totally antisymmetric states will be either spin singlet and valley triplet, so antisymmetric times symmetric, or vice versa. And here you can see that this is 1 times 3 plus 3 times 1, this is 6. And now I can actually write these projection operators just as I did before with basically S1, the spin projectors I will write as S1.S2. And the triplet is just minus this one minus this projection. And the same for the valley, and I call the valley operators tau and tau1 and tau2. So if I do all this, I get this, this Hamiltonian. Okay, so this is the prescription. This is the projection operator onto the singlet, onto the triplet, for the spin, and the same I do for the valley. Okay, so then we find this Hamiltonian, and then we think we have something new, and then you go and you look into the literature, and you find that in the 1970s, there were some Russian theorists, they already knew about this. Yes? Yes, here I assume that they're degenerate, although you can make this more general, where they're lifted. Of course, if they're lifted by a large energy, you can again forget about it. But if they're lifted only a little bit, then you can modify this. This is actually what Kugel and Kamsky did. So in some sense, they solved an even more general problem than we did. This was for a completely different system. This was for a highly correlated system with d orbitals in some kind of compound. But basically, this is a special case of their Hamiltonian. Okay, so I'm almost done. So, I mean, now the question would be: so if the valley splitting would be 0. If the valley splitting was 0, so can we do quantum computing with this? And I mean, the valley sort of gets in the way. You see that this contains coupling between the spins, coupling between the valleys, but also coupling between spins and valleys. So this will create some spin-valley entanglement, and if I don't really control the valley, that's probably going to be bad. It's easy to see how you get the time evolution of this. This is again a projection operator. You can easily exponentiate it just in the same way as we did this morning for the exchange coupling only, for the spin only. You can make some sort of swap if this integrated exchange is pi, and actually that works. You can swap both spin and valley with this. And then you can also do square root of swap if phi is pi half. So now you could think, well, okay, that's it, we have it, we can do square root of swap. But the problem is, swap is really a tensor product of swap for spin and swap for valley. That's good. But a square root of swap is the square root of a product, and this is not the same as the product of the square roots. And that's the problem. So then I cannot do spin-only quantum computing with this Hamiltonian. I have to do, so basically I cannot use the sequence that I showed you this morning, the spin square root of swap. But then, okay, I used to have a very good student, Niklas Rohling. He's now not in Constance anymore. He's in at NTNU in Trondheim in Norway, working with Arne Bratas on spintronics. And he found another sequence, basically, where you can make pure spin swap by making half, sort of basically a 4th root swap, and then making an X rotation. Sorry, I should probably start here. You have the Z rotation, you make a 4th root swap, then you make an X rotation, and then another 4th root swap, and you have to do it twice. So in principle, you can do pure spin quantum computing with such a valley degenerate system. Of course, it means here, this would mean that you have to be able to rotate the valley degree of freedom. And that's not, maybe not so easy. Of course, so this would allow you to use only the spin, or actually by symmetry, also only the valley. So in principle, you can also use the valley as a qubit. If you think the valley is coherent, you could use it. I think the valley is probably not as coherent as spin. And here's, and actually then Niklas found another scheme where you can use even both spin and valley. So in some sense, one electron in graphene or silicon gives you 2 qubits. It has a spin and it has a valley. If they're both coherent enough, then you could use both of them for quantum computing. And in principle, this can be done. And this can be shown. Basically, I mean, you have basically you get some operations you get for free, and this is actually using a spin singlet-triplet qubit encoding. Okay, but I'm not going to go into the details. Okay, so I think I'm going to stop here. So the next topic I want to touch upon is spin relaxation. I can show you maybe the difference of that different materials make. So I will show you the basic principles of how spin relaxation works in semiconductors typically. And I will also show you what is different between, let's say, gallium arsenide and graphene or silicon. But I think this will be for tomorrow. And so I thank you a lot for your attention, and see you tomorrow. Or maybe you have more questions, actually.
So can you just remind me how things are different in the case of carbon nanotube? Because some of these issues should come up also with carbon nanotubes, right? The things that you were discussing. For
right.
So, and those are used carbon nanotube quantum dot circuits
yes.
all the time. So can you
right.
explain a bit?
So carbon nanotubes are very similar to graphene in that they also have valley splitting. So they basically inherit the valley splitting from the graphene that they're made up of. One difference is that carbon nanotubes have the curvature in carbon nanotubes. If they're sort of small radii carbon nanotubes, they tend to have large spin orbit coupling, relatively large spin orbit coupling, whereas in graphene the spin orbit coupling is almost zero. And so this means that spin and the valley are already coupled at zero magnetic field. So this is a bit similar to the transition metal dichalcogenides we heard about this morning, that the spin and valley are locked because of spin orbit coupling. This also happens in carbon nanotubes and not in graphene. But the valley degeneracy is, I would say, is the same. Yeah, I'm also wondering. It's a good question. I think probably, so long wavelength charge noise probably doesn't matter because, you know, these valleys, they are very far apart in the Brillouin zone. So it means then if you look at the average, at the charge density, they don't really, I mean, the charge density of two states in these different valleys doesn't really differ. It's only if you look sort of from one atom to the next, if you look at the phase relation of the wave function. And I think long wavelength charge noise cannot see that or cannot couple to that. So it would either be some kind of really short range, short wavelengths, but this would be X-ray, so I think it's basically out, I don't know. Or if the valley couples to something else. So in silicon, for instance, there's this valley orbit coupling, which means that the valley, so the quantum dot eigenstate wave functions are slightly different in the two valleys. And then, of course, you couple again to charge noise. But to be honest, I don't really know. I mean, I don't think we know. I think it's still a good question. I think the most we know about valley coherence comes from the transition metal dichalcogenides, where we can really make these superpositions with optics, and you can see how long it lives. And so on. Yeah, so when comparing these different qubits, I think you cannot order them in a 1D space because, I mean, of course you can order them by coherence usually, but then of course it's always a trade-off between coherence and how well you can do operations. And so, I mean, I like the exchange-only qubit very much, where you can switch off all the couplings and then it's a pure spin. But that may not be the best realization for electric control.
So what would be how would you go about, because even for exchange only, there were few different things you were considering with 2 dots and 3 spins, and there were all sorts of other options.
So I think from my point of view would be that exchange only without leaving the exchange couplings always on would be best, particularly if you want to use this for memory. And then only switch on the exchange couplings when you want to couple, when you want to make gates or couple to a cavity. But maybe when you ask an experimentalist who tries this and then tries all the other options, maybe then there's another trade-off. So ultimately I don't know. I think what we can offer, also you have this overhead of 3 times more spins and quantum dots and maybe 10 times more pulses compared to the single spin qubits. So it's also a question of whether this pays off, right? Whether this spending this overhead really pays off in terms of scalability and coherence and so on. So this I don't know.
Could you say something about how you would read out the exchange-only qubit? Because you need to distinguish between the 2 states.
Yeah, so the question is about readout of the exchange only. And actually that would be very similar to the readout of the singlet-triplet. So the singlet-triplet you could read out by just tilting the potential and see whether the charge goes over. Right? So the singlet would go over and the triplet wouldn't, and then you would do charge detection. And it turns out that the exchange only has the same feature. So maybe I can show you. Yes, so if you look at these states, you will see that this state is a spin up in the middle dot and a spin singlet in the outer dots. And this one is a spin down, okay, either down or up, and it's always spin triplet. This is spin triplet in the outer dots, and this is spin triplet T0 in the outer dots. So, okay, now it's ordered in a way which is maybe not so good for readout. You could also reorder, you could, exchange the position of these 2 or do a swap. But then you would have next to each other 2 dots in which you would have either singlet or triplet, depending on whether you're in 0 or 1. And then you could do exactly the same readout, spin to charge conversion and readout.
Okay, so if we don't have any further question, let's thank the speaker one more time.
Thanks.